Okay, welcome everyone. My name is Emily Moravik and I'm a postdoc here at Green Bank Observatory. Thank you for joining us today for this proposal planning workshop. So today I'm going to start off giving you a welcome and an overview of GBT science and capabilities. Please do take a few moments to fill out the poll that we've put in the chat. And the answers to two of the fun questions will be hidden within the presentation, so you can find the answers. So the goal of this workshop today is to train new users on how to propose to use the GBT, to update our community on the current capabilities, and address any of your questions about how to submit a proposal. We changed the schedule a little bit. We switched around a few sessions, so here's the updated schedule. And I'll also note that we're having an office hour next week, and this is primarily for those who are in different time zones that couldn't make it today, and will then watch this presentation and then come and ask us questions. And we will make recording of this talk and all of the talks today available after the fact today. So I'll be talking about a few different things in this first hour here, a basic overview, introduce you to the different science areas that scientists use the GBT to study, the capabilities and performance of the GBT, explain a few of the most common observing strategies, and then also go through the current 22B proposal call. So I wanted to first note that Green Bank is the original NRAO site and has been operating many world-class telescopes for quite a while. So here are a few photos of the ones that are on site, and the main one is in the center. That's the one we refer to as the GBT. It was completed in 2000, and there was an upgrade in 2009 to improve high frequency observing. So one of the unique things about Green Bank Observatory and the GBT is that it's located in the National Radio Quiet Zone, which is a very large area that encompasses the Green Bank Observatory and also a Navy facility, a US Navy facility in Sugar Grove. And this was established by the Federal Communications Commission and the Interdepartmental Radio Advisory Committee in the 1950s to minimize possible harmful interference from transmitters such as wireless communications, personal mobiles, aviation, radio broadcasts, and satellite transmissions. And so this is to reduce the radio frequency interference, or RFI, that will affect a lot of the bands that we use on the GBT and just GBT data in general. So some of the key capabilities of the GBT is that it's a 100-meter diameter unblocked dish of aperture. And so that simply means that the feed arm is in a position such that it does not block the radiation that comes in, where you see this image on the right that some previous telescopes have those arms that block the light coming in, and that can affect your image analysis. So the receivers cover a wide range of the frequency space. You can see in the lower right-hand corner a plot comparing the GBT coverage to that of the VLA and ALMA. And due to the large dish capabilities, we have excellent sensitivity for point source and extended objects. And we cover about 85% of the total sky. And as I said before, this is a key part that we're in the National Radio Quiet Zone. So RFI is mitigated here. So that's an excellent point. If you do have questions during the presentation, please do put them in the chat box. We have several of our scientific staff here to answer your questions. Another interesting and important part of the GBT is that there are 2004 panels, and on each of the corners of the panels are these actuators. And this allows us to send corrections to the dish to increase the capabilities of high frequency observing. So deformations due to gravity, temperature, and wind can really affect high frequency observing. And so we can send corrections to these actuators and correct for these deformations. The GBT is fully steerable, so it's on a track and it has these azimuth wheels that makes it fully steerable. And the elevation limit is about 5 degrees. However, we recommend for those observing around the water lines and higher frequency that it's about 15 degrees of an elevation limit. You'll want to keep slew rates in mind if you're observing a lot of sources. So the max is 40 degrees per minute, but the average is about 35.2 degrees per minute. And we note that when the temperature hits about 17 degrees, we have to go to half slew rate because the oil in the wheels actually begins to freeze. And when it goes below, I think it's -10, we have to stop observing because it becomes solid. And then the max for elevation slew rates is 20 degrees per minute, but average is about 17.6. So here is a brief summary of all of the science topics that scientists use the GBT for. A lot of people use it for studying pulsars, particularly nanograv, who their collaboration has guaranteed time on the GBT. Scientists use the GBT to study neutral hydrogen and high redshift in cosmology, such as galaxy clusters. Scientists also use it to do astrochemistry. So it's a very popular topic currently. Also, masers and star formation are big areas that have produced a lot of papers for the GBT. Scientists study basic physics and solar system astronomy using the GBT. And Breakthrough Listen is another big project that uses the GBT and has guaranteed time on the GBT. And then lastly, the GBT is used to study fast radio bursts. So there are a lot of topics that you can use the GBT to investigate things for your science. So every 10 years, the National Academies of Sciences, Engineering, and Medicine collects information from the astronomical community to decide what are the most important things to study in the next 10 years in astronomy. And the GBT was mentioned and really endorsed well in the decadal report, specifically highlighting some of these science areas that I mentioned before. And so, yeah, the decadal report really endorsed GBO and GBT. And as a part of the decadal survey process, the community can submit white papers to say what they think is important to study in the next 10 years. And here's a summary of how the GBT was mentioned, whether it was explicitly or implicitly. So a lot of the community really supports using the GBT for their science. So here's a quick summary of some of the various just facts about the GBT that you might be interested in checking out. A lot of these things that I'll be showing are all in the proposer's guide. So let's talk about the available receivers that you can use for your science. We have the prime focus receivers and the Gregorian receivers. So the prime focus receivers are put on this retractable boom, and only one can go on the telescope at a time. And they're low frequency receivers. And so these have to be manually changed out. Whereas there are the Gregorian receivers, which are in this turret that can move. And there can be 8 on the telescope at a time. So the prime focus receivers, you have the light collected by the dish, and then it goes directly to the prime focus. So they collect light there. Whereas the Gregorian receivers use the subreflector. So you have the light collected by the dish, goes to the subreflector, and then into the Gregorian receivers. So for the prime focus receivers, we have 4 different receivers currently that are listed here. The most popular ones are the 342 and 800 megahertz receivers. The 450 and 600 receivers overlap with TV signals, so there's a lot of RFI. So you can use it, but you should contact a support scientist before if you'd like to use and propose for using this receiver. There's also a receiver, the Prime Focus 2, that has a various bandwidth options. And I'll note that we need a maintenance day to switch out the prime focus receivers. So that happens once a week. And so that regulates the availability of each of the receivers. We have a new receiver coming online soon, the ultra wideband receiver. Has a very wide instantaneous bandwidth. It's been optimized for high precision pulsar timing and wideband observations of fast transients. So it's going to be commissioned during the spring and summer, and this will affect the availability of some of the prime focus receivers. So we anticipate that it will be ready for the 23A call, but if you're interested in using it for your 22B proposal, you can indicate that you're interested in using that if it comes online instead of the main one that you propose for. So these are the 11 Gregorian receivers that are possible or that you can propose to use. And I'm just going to go through each one of them and note some interesting things about each one. So we have L-band that you can use a notch filter in that will suppress some of the RFI. So you may see that option in your observing scripts or in the proposal tool. C-band, we only recommend linear polarization currently, so that's just for your information. For X-band, the polarization purity degrades above 10 gigahertz. You can observe up to 11, but the polarization purity degrades. And we're commissioning a new X-band receiver this year sometime. KU band has 2 beams that you can use. And then KFPA, this is a multi-pixel receiver, and you can use it in narrow or broadband mode. But if you use it in broadband, there's only 1 pixel or beam available. KA band also has 2 beams, and it's separated into 3 subbands. Q and W band also have 2 beams, and W band is also separated into subbands. And then Mustang 2 is an interesting instrument. It's a bolometer camera that was developed and commissioned by the University of Pennsylvania. It's essentially a continuum instrument. And you have to have the permission from the Mustang instrument team to propose and to use it. So just reach out to us if you're interested in using that, and we can give you the contact information. Or if you just look on the website, you'll see the information there on how to contact the team. And there's also Argus, which is a multi-pixel receiver, has 16, and it is single polarization. So that's a brief overview of the receivers that we have available. So there are 2 tables that will be of use to you in the proposer's guide that give you a lot of the just stats and different bits of information about the receivers. And it also includes information about the performance and bandwidth of each receiver. So we note that the availability during each semester of the receivers changes, and this is based on the proposal pressure and the pressure that is applied based on high-ranking proposals. So if you have a lot of proposals that ask for a specific instrument, that one is going to be up on the telescope a lot of the time. But some of the most popular receivers are L-band, X-band, Mustang 2, Argus, and KFPA, and those are on the telescope usually all the time. In this next coming semester, the 22B, the Prime Focus 800 will be available irregularly due to the new receiver testing. And we're going to be commissioning a new X-band receiver in the spring and the fall, or the spring and the summer. So some of the less popular receivers, but they would be available if a high-ranking proposal came through, are these that we have listed here. So the 342 S-band, C-band. So those would be swapped out on a maintenance day to be on the telescope for a certain period of time for those high-ranking proposals. So what you should take away from this is that there are some that are very popular, but the proposal pressure and the high ranking proposals specifically determine what will be on the telescope at a given time. So here are the available GBT backends. So you have Vegas, which is the most used. You have a continuum, 2 different continuum backends, a VVL-BA and radar backend, and then also you can request to use the breakthrough listen. It's about 50 hours a semester that you can use the breakthrough listen backend, but again, you have to contact the team to ask for that. So I'm going to go through a few of these backends to give you some information about them. So you have the Vegas spectral line mode. So again, this is one of the most popular, if not the most popular, just backend that's used. So it has 29 modes, and the bandwidth and spectral or velocity resolution that you want determines the mode that you use. So that's all listed in this table here. And modes 20 through 29 use subbanding. So you can have up to 8 subbands. So these are the modes that you'll put into the sensitivity and mapping calculators and the proposal submission tool. So what to take away from this, just identify the bandwidth and spectral resolution you want to determine the spectral line mode that you'll use with Vegas. Vegas also has a pulsar mode, and you can do coherent or incoherent dedispersion modes. There are various bandwidths that you can use and a number of channels. So you can contact our support staff if you need help with determining which different set of parameters that you want for pulsar mode. So I'm going to go over a bit of observing strategies because this will determine what you need to put into your proposal and the information you need to provide in the proposal process. So there are a lot of options for observing strategies. So this is a quick checklist on what you need to think about when you're putting your proposal in. So pick your receiver based on the frequency that you want to observe. That should be pretty easy. You know what you're observing, you know what your science is, so choose your receiver based on that. And then you pick the back end based on the observing type, spectral line, continuum, pulsar, etc. And then you'll pick your observing techniques based on your science goals. So I'll be going through some techniques to help you know which technique to use. And then also your calibration strategies will depend on your receiver and science needs. So high frequency, you have to do something called auto-oofing or oofing, where you have to determine deformations in the dish due to gravity and wind and temperature. And that whole process takes about a half hour. And that's done at high frequencies. And then Gregorian receivers, you have to do focus corrections because you're not at prime focus. And then the prime focus receivers, you don't have to do any focus corrections because you're at the prime focus. So these are the various things you need to consider when you are proposing for time on the GBT. So there are 3 different observing modes that you can use to derive your reference data. Frequency switching, position switching, dual beam position switching. So I'll go through each of these to help you understand these different observing strategies. So the first is frequency switched observations. So this is where you obtain blank sky information by keeping the telescope pointed at an object of interest, but then switching the center frequency of the measurements. So you're switching the local oscillator. So on the left, you can see an image or a spectrum with the 2 different positions of the line. And so this only difference is that the local oscillator has been switched and shifted. So something that's important about this is you need to have a priori information about the redshift of your object. You need to know that pretty well for this to work well. And so then you take a difference and you get the right image, and it's your line of interest, but shifted by the amount that you have shifted the local oscillator. And so it's much more complicated than just differencing and adding or averaging to get your final spectrum, but that is the general idea. And you can have in-band or out-of-band frequency switching. So in-band is when you move the signal or the local oscillator by an amount that stays within the band, and then out-of-band is when you move it enough that the line will actually go out of band. So that is frequency switching. So the use cases are if you want to have a lot of on-source time and you have a well-constrained redshift of the object, as I mentioned. So you need to really know that pretty well so that you can keep track of how much, where the line is and then when it's shifted and such. So a good use case is narrow line observations in a clean spectrum so that you can really keep track of when things are shifted and make sure you know what's going on. And a lot of people use it for galactic H1 observations. I've listed some advantages and disadvantages here. So it's nice to use frequency switching because you're always on source, and so you don't lose any time going off source. But you do need to know the redshift in advance, and the system has to be stable enough to get good baselines. So another type of observing strategy to define your reference data is position switching. So this is where you are on source and then you move the telescope off source. It's never as much as I have here, but just for illustration. What that looks like is you have on source, you have your source and all your noise and everything else, and then you go off the source and that's just everything else. You actually notice that there's a little blip at about 4,500 kilometers per second, and that's actually the line that we are interested in. So you effectively take the difference between these and you get your line of interest. So that's how position switching works. Position switching gives you a really good baseline. So the use cases for position switching is when you have a narrow line and you have crowded spectral region or RFI. You can also do this when you have broad lines, and this is when you want the best baseline measurements as possible. And it's good to do this when you have compact sources. So these are just a few guidelines for when to use each. Again, I've listed some advantages and disadvantages. It's nice with this because you need little a priori information about the object. So if you don't know the redshift, and the disadvantages are you're moving the telescope, off source, so that takes time. And then the last observing strategy that I'll talk about is dual beam position switching. So there are two different types. So for this, as indicated by the name, you need two or more beams to do this. So you can nod, which is where you're moving the telescope such that you're moving the source between the different beams. So you're always on source, but you're still getting reference data with one of the beams. And then there's sub-beam nodding, which is when you're using the sub-reflector to use or to move your source between the beams. So the use cases here are you have to have a multi-beam receiver, and it's useful when you're observing a small angular source because you need to make sure that if you have an extended source, this doesn't really work because you would have to go really far away from the source to get away from both beams of the receiver. So that's a quick overview of the various types of observing strategies that are used with the GBT. You have frequency switching, position switching, and dual beam position switching. And so if you need help determining, you can just contact the support staff. So a few more words about observing strategies. So if you have a small source, here are some of the use cases, some of the observing strategies you would do if you have a small source. So if the source is less than the size of the beam and it's a line observation and you're using position switching, For K and W band, you would use nodding because I have two beams. For KA, Q, and Argus, you can use sub-beam nod. If you're just using a receiver that has one beam, you can do these on-off, which indicates the usual position switching where you're on the source and then off the source. That's what on and off means if you see that. Then you can also do tracking, which is where you go with the source and you track the source, and then you do an offset. So you have the source plus some offset to get the reference data. And then if your source size is less than the beam size, you're still doing line observation and you're doing frequency switching, you'll also have a track scan. And then if your source size is less than the beam size and you're doing continuum observations, you'll use daisy mapping. Now, it may seem that why would you be mapping if you're doing a continuum observation, but it's actually been found that this is an efficient way to deal with the 1/f noise that comes with a broad bandwidth. So if you're observing a larger source, much more extended source, and you're doing a map that is larger than the field of view of the instrument, you'll do an RA or DEC lawn map. That you'll be putting in the mapping calculator, which we'll show you later. If the map size is less than or equal to the field of view of the instrument, you might do either RA or DEC mapping. You might also do a daisy map. That gives you high sensitivity near the center of the map. So if you're interested in a central point source, that might be the best choice for you. And a point map is just where you have this RA and DEC map on the fly, and you're continuously taking data points. So something that's very important for you to think about in your proposal process is you need to estimate the overheads, and you need to clearly explain that in your proposal. So there are a couple of different guidelines that we're giving here. So you should point and focus every 30 to 60 minutes, depending on your frequency and the time of day. So this takes about 5 minutes. So I've listed here the recommendations for each of the bands. So as you can see, it varies how often you should do this based on the receiver. And then high frequency observing, as I mentioned before, requires auto oofing, which takes about 30 minutes. And you have to do it every 2 to 4 hours usually. And again, it's these high frequency receivers. So you need to really state your overhead estimates in your proposal, specifically under the technical justification. There's a box there that you need to say what you did for your overhead estimates. And our staff goes through and checks those after proposals are submitted. So here are some guidelines for creating your sessions. So part of the process in using the proposal submission tool, which one of my colleagues will be going through later, is creating sessions. So you'll have, if you have more than one source, it's usually a good idea to group them into sessions. We've seen it before where some of the mistakes people make is that they don't group their sources at all. So we do recommend grouping them into sessions. And here's some advice for doing that. So keep in mind that we only ever do 15-minute increments. So you can't do a session that's like 2.12 hours or some such thing. Sessions should be less than 6 hours to make them easy to schedule. And in each individual session, you should include receivers and backends that are used together in a single observation. We recommend that sources should be within 2 to 3 hours of each other in RA, that they should be visible for 1 to 2 hours at the same time. So this is the makeup of a good session. And then the declination should be within tens of degrees of each other. And lastly, we don't recommend putting sources that are really far apart together. So things that have declinations above the latitude of the GBT are northern sources, and those that have less than the latitude are southern. And if you have a long distance between the two, you could hit the end of the wrap of the telescope, and you'll have to unwrap the telescope, which can take 5 to 7 minutes. So we recommend putting sources that are, relatively close together so that you don't end up accruing more overhead time in this. So this information is also listed in the proposer's guide for you. So I'll briefly go over the proposal call. So the deadline is in a few weeks, February 1st at 5 p.m. Eastern. There's the proposal call link. The disposition letters will be sent out in late May this year. So if you submit a proposal, keep an eye on your mailbox around late May. And the observations will be August 1st, 2022 through January 31st, 2023. We have a training school that would be held in late February. The applications have already closed for that, and it'll be fully virtual, but we do several a year. There's also a single dish school. If you're new to radio astronomy, that'll be in May, and it will most likely be hosted at Arecibo. So that'll be a good training opportunity if you're new to radio astronomy. I'd like to note that the GBT is a part of the joint proposal program. So you can propose to use the GBT and another telescope. So you can either propose to use the GBT and ask for time on something else. So that would be where the primary is the GBT, or you can propose to use another telescope as the primary and also ask for time on the GBT. So here I've listed each of those cases and then how much time is available to the other telescope based on where you submit it to. So that's all listed there on that link that I've put there that you can find in the slides after. There are two different types of proposals, the regular and large proposals. And they're grouped based on the number of hours or the duration. So if it's a lot of hours and much longer, it's a large proposal as to a regular. And as of a few years ago, it was true that large proposals could only be accepted in the February deadline. So it's a February deadline, so you could submit a large proposal. There are also triggered and DDT proposals. So triggered proposals are where you submit at the normal proposal deadline, but they are intended for observations of transits whose start times are not known a priori. So you can say, I want to observe this target if it starts. So like the radio bursts, the fast radio bursts, you can submit a proposal to say, these are the triggering conditions, and I would like to observe it for this long. So, but you really need to be clear and justify your trigger criteria so that then we can make sure that your object gets observed at the right time. There are also director's discretionary time proposals. So these are for target opportunity or they're exploratory. So it's if something that new has popped up, it's unexpected and you need a rapid response time, and we didn't know about this object till right now, and you really need to observe it right now, you can submit a DDT, and this is not at the typical proposal deadline time. It can also be a pilot study if it's just a few hours, just needed a few hours to explore something that then you could use to put in a regular proposal later. We also have the GBT is part of the VLBA or the VLBI, and including the GBT in those observations will improve sensitivity. This is the back end that you use, and you do need to include overhead estimates as before. And one thing that people I think forget is that there's startup time that you need to use for setting up and pointing for VLBA observations. So there is more information that can be found here at these links. So for data reduction and observation, so successful proposals will be observed by the PI or another member of the proposal team. So we have training schools for people to learn how to become an observer and become certified to be a remote observer. And we have these typically in January and February, May and September. It's becoming more common now that there are operator run projects. So you can consider if your project can be operator run, but it can't be one that requires AutoOOF. We also have data reduction products that should be and can be used to help you reduce your data. So you have GBT IDL for spectral line data. And then we also have a data reduction pipeline that you can look into as well that's very useful for mapping, for reducing maps. So here is a checklist of the things that you need to consider before submitting your proposal. We wanted to create a checklist for you so that you could make sure you have everything when you go into the PST or you're not surprised by something. So you need your scientific justification. The page length is based on if it's irregular or large. So this is where you describe why you want to, what you want to observe, why you want to observe it, why you need a certain time, or why you need the total time on the telescope. The technical justification section is where you'll justify your total time request. So you'll need to have your time on source, which is the output of the sensitivity calculator, how much time you'll need to make a map, which will be the output of the mapping calculator. You'll also need to include your overhead calculations in this and describe that. You'll also have to talk about the impact of RFI on your data, if any. You'll need to group your sources into sessions. So you'll have to give a list of your sources, and then you'll have to group them with receiver and backend information. And you'll also have to have your resources, which are your where you put in the backends and the receivers that you're going to use. So this is some brief and broad information for you in your proposal planning process. I hope this has been useful to you, and we'll take a moment to answer any questions that you might have about general capabilities. My colleagues are going to go through the mapping and sensitivity calculator and also through the proposal submission tool and help desk. So those things the questions like that will save. But if you have any questions, please do put your questions in the Q&A or boxes or raise your hand, and our staff will read the questions, any questions that have come in and answer them. So let's go ahead and do that. Let's see, do we have any questions? Don't be shy about asking questions. Looks like we had an answered question already. No questions. Okay, I'll wait maybe another minute or two. Oh, great, there's a question. Can you explain in more detail the 16 pixel receiver? I'm going to defer perhaps to Ryan or Bryn in this one to describe it a bit more. If there's anything you're particularly interested in, please let us know. But I'll have one of my colleagues describe that a bit more. Ryan, are you raising your hand to do that? You are not, you're muted.
There we go. Sorry, I hit the button, but it didn't actually work. Yeah, so I said to the best of my ability with caveat that most of my observing is down at low frequencies, observing pulsars, so not up to 3 millimeters with Argus, but I do know the basics. So I think you're referring to the 16 pixel Argus receiver. The operating frequency range is about 75 to 116 gigahertz, and you can find the exact frequency range in the proposer's guide. That is not the instantaneous bandwidth. The instantaneous bandwidth is limited to smaller windows that you can tune across that band. And it does have 16 pixels, single polarization, so it's not dual polarization. So you can't use it if you're interested in studying polarized sources, but for unpolarized sources, you have one channel per beam. It is a sparse array, so it's basically 16 individual feed horns. So the pixels on the sky are not completely evenly filled, but for mapping experiments where you're moving across different regions on the sky, you still would cover the full region that you would want. And so I think most of the science there is mapping dense gas, looking at like CO and some other dense gas tracers. If you have any other more specific questions, you can put it in the chat or the Q&A, and I'll do my best. And if I don't know the answer, then we will find the person who does.
Great. Thanks, Ryan. Yeah, so if you have more questions about that, please let us know. So we had a question in the Q&A. Thanks for a great presentation. Is it planned to replace the auto-OOF procedure with a Lassie scan? And if so, when will this be implemented? So I'll let Pedro, our Lassie expert, speak to this.
Thanks, Emily. Thanks for the question. Truth is, the answer is a bit complicated. So, well, first thing, what is Lassie? So it's a terrestrial laser scanner that basically is able to map the surface of the telescope, of the primary reflector. And based on these images, one can find how the primary reflector has deformed and then use the actuators to correct for this deformation. So it basically tries to do the same thing that autofocus holography does, but using a terrestrial laser scanner. We're still not very clear on if we will be able to replace auto-OOF with Lassie. There's not a clear answer yet, and for the same reason, I can't speak about if this will become available or when it will become available in the future. But it's something we're still investigating. We'll let everybody know as soon as we have a more definite answer. Thank you.
Thanks, Pedro. Okay, so we have another question in the Q&A. What is the minimum signal to noise ratio of signal that we can receive at GBO? I think we'll need a bit more specific information because it will depend this will also really depend on your science. What is the minimum signal to noise ratio that you can tolerate in your data and what your science is? So yeah, and they're different, receivers will have different noise levels too. I don't know if any of my colleagues have anything to add to that, but I think we would need a bit more specific information on that question. Okay, we have another question, but for dual beam position switching, why is it that nodding is used for some multi-beam receivers while solid beam nodding is using for others? Yeah, that's a great question, and I actually asked it earlier last week. It just depends on the receiver, which one you're using, if it's possible, if you can do that. And it also depends on the throw of the subbeam, the subreflector. So if that amount that it moves puts it out of the area that the receiver is observing, then you can't use it for that receiver. So it really just depends on the receiver that you're using. And so I can't remember off the top of my head which one is which, but if you have a question on which receiver you should use each thing, definitely please ask one of our staff when you're writing your proposal. We have another question. Will the flag receiver be available this semester? I don't know about that one, so I will defer to my colleagues again about that one.
Yeah, so I was actually just answering this in the text. There's no plans to offer flag. However, since you asked, if you're interested in multi-pixel or phase array feed mapping at L-band on the GBT, I would encourage you to contact DJ Pisano, who's a professor at WVU. There are some possible plans for moving the alpaca phase array feed that was planned for Arecibo to the GBT. And DJ, I should say, is collecting potential use cases for that. And if you have some in mind, or if you would like to contribute to that discussion, then you can reach out to him. I want to stress that that's something that's being discussed, nothing that's definite at this time.
Okay, great. We still have a few more minutes before our scheduled time, so we have some time for a few more questions if anybody has more questions.